There's a question that has haunted scientists for over a century, and once you hear it, it will haunt you too. If you're travelling at the speed of light and you turn on your headlights, what happens to the light? Does it shoot ahead of you? Does it stay trapped inside your headlight? Or does something far more bizarre occur that challenges everything you thought you knew about reality? This simple question, first posed by a 16-year-old Albert Einstein, would eventually shatter our understanding of space, time, and the very fabric of existence itself. But to understand why this question is so dangerous to our perception of reality, we need to go back to a time when humanity believed something completely wrong about light, something so fundamentally incorrect that it shaped thousands of years of human civilization. The Great Deception. For most of human history, light appeared to be instantaneous. When you flicked on a candle, the room illuminated immediately. When lightning struck, you saw the flash at the exact same moment you heard the thunder. When the sun rose, its light seemed to reach your eyes the instant it appeared over the horizon. Everything in human experience suggested that light simply had no travel time at all. But here's where it gets fascinating. Ancient Greek philosophers like Empedocles and Plato actually believed that vision worked by light rays shooting out from your eyes like invisible lasers scanning the world around you. Think about that for a moment. They thought your eyes were flashlights, not cameras. This wasn't just a random guess. It made perfect sense based on what they observed. After all, when you close your eyes, you can't see anything. When you open them, you can see instantly. To them, it seemed obvious that your eyes must be actively reaching out to touch the world with light. This fundamental misunderstanding about light being instantaneous became deeply embedded in human thinking. Aristotle, one of history's most influential philosophers, declared that light had no speed at all. It simply existed everywhere simultaneously. For nearly 2,000 years, this idea went unchallenged because it matched perfectly with human experience. But what's truly remarkable is how this wrong assumption shaped entire civilizations. Navigation, architecture, astronomy, even the way we think about cause and effect, all developed under the assumption that we see things exactly as they are, exactly when they happen. The idea that there might be a delay between an event occurring and us seeing it was literally unthinkable. Here's what makes this deception so perfect. In everyday life, light is so fast that it appears instantaneous. When you're looking at objects across a room, light travels from those objects to your eyes in about 10 billionths of a second. Your brain can't even begin to process time intervals that small. So for thousands of years, humans lived in a universe where cause and effect seemed perfectly synchronized, where seeing was truly believing, and where light was considered the one thing in the universe that had no speed limit. The first crack in reality. The first crack in this perfectly constructed illusion came from an unexpected source. In 1676, a Danish astronomer named Ole Rømer was doing something that seemed completely routine. He was studying the moons of Jupiter, trying to create better maps of their orbits so that sailors could use them as a cosmic clock for navigation. But Rømer noticed something impossible. Jupiter's moons weren't keeping perfect time. When Earth was closer to Jupiter, the moons appeared exactly when his calculations predicted. But when Earth was farther from Jupiter, the moons were consistently late. Not just slightly late, but predictably, measurably late. Now, this created a massive problem. Moons don't slow down in their orbits. The gravitational forces that control planetary motion are incredibly precise and consistent. There was no known force in the universe that could cause Jupiter's moons to suddenly start orbiting slower when Earth happened to be farther away. It made absolutely no sense. But Römer had a radical idea. What if the moons weren't actually late? What if they were eclipsing Jupiter exactly on schedule, but the light carrying that information to Earth was taking longer to reach us when we were farther away? What if light itself had a travel time? This was revolutionary thinking. Römer was suggesting that when we look at the universe, we're not seeing what's happening now, but what happened in the past. The farther away something is, the further back in time we're seeing it. When Earth was on the opposite side of the Sun from Jupiter, we were about 186 million miles farther away. If light had a finite speed, it would take longer to cross that extra distance. Römer calculated that light from Jupiter's moons took an extra 22 minutes to reach Earth when we were at our maximum distance. Based on this observation, he calculated that light travelled at about 140,000 miles per second. This was the first time in human history that anyone had measured the speed of light, and it revealed something profound. Light wasn't instantaneous, it had a definite, measurable speed. But here's what's truly mind-bending about Römer's discovery. He had proven that everything we see in the night sky is actually a time machine. When you look at the moon, you're seeing it as it was 1.3 seconds ago. When you look at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. When you look at the nearest star beyond our solar system, you're seeing it as it was over 4 years ago. Römer had discovered that the universe we see is not the universe as it exists now, but a museum of the past, with more distant objects showing us increasingly ancient history. This was the first hint that space and time might be connected in ways no one had ever imagined. The measurement revolution. Römer's discovery sparked what can only be called a measurement revolution. Scientists across Europe became obsessed with determining the exact speed of light. They devised increasingly ingenious experiments, each one revealing new layers of complexity about this mysterious cosmic speed limit. In 1849, French physicist Hippolyte Fizeau created one of the most elegant experiments in the history of physics. He placed a bright light source behind a rapidly spinning gear wheel with hundreds of precisely cut teeth. The light would shine through the gaps between the teeth, travel several miles to a mirror, and reflect back to the observer. Here's the brilliant part. If the wheel was spinning at just the right speed, by the time the light made its round trip, the next tooth would have moved into position, blocking the returning light. By carefully adjusting the spinning speed until the light was completely blocked, Fizeau could calculate exactly how long the light took to travel his measured distance. His result? 195,000 miles per second. This was remarkably close to the true value, and it proved that you could measure the speed of light right here on Earth, not just by observing distant planets. But Léon Foucault, another French physicist, took this even further. He replaced Fizeau's gear wheel with rapidly rotating mirrors. As light travelled from the source to a distant mirror and back, the rotating mirror would have turned slightly, causing the returning beam to hit a different spot. By measuring this tiny deflection and knowing the mirror's rotation speed, Foucault could calculate light's travel time with unprecedented precision. What's fascinating is that every measurement using completely different methods kept converging on the same impossible number, approximately 186,000 miles per second. This wasn't just fast, it was unimaginably fast. Light could circle the entire Earth more than 7 times in a single second. It could travel from New York to Los Angeles in about 16 thousandths of a second. But here's what puzzled scientists the most. Why this specific number? Why not 100,000 miles per second or 500,000 miles per second? In a universe where speeds could theoretically be anything, why did light choose this particular velocity? There seemed to be something special, something fundamental about this number that went beyond mere measurement. Each new experiment revealed more precision, but also more mystery. Scientists were measuring something with incredible accuracy, but they had no idea what they were actually measuring. They didn't know what light was made of, how it travelled, or why it moved at this specific speed. They had discovered a cosmic constant, but they had no idea what it meant. The measurements also revealed something else troubling. Light speed seemed to be absolutely constant. It didn't matter how bright the light was, what colour it was, or what it was shining through. The speed never changed. This constancy was unlike anything else in physics. Most things in the universe could speed up or slow down depending on conditions. But light seemed locked into this one specific velocity, as if the universe itself had set an immutable speed limit. As the 19th century progressed, scientists had succeeded in measuring light's speed to extraordinary precision. But in doing so, they had opened a Pandora's box of questions that would soon reveal that their understanding of space, time, and reality itself was fundamentally flawed. They had measured the speed of light, but they were about to discover that they had actually measured something far more profound, the speed at which reality itself operates. The stage was now set for a discovery that would change everything. Scientists had proven that light had a definite speed, but they still believed it must be travelling through some kind of medium, just like sound waves travel through air. They called this invisible medium the luminiferous ether, and their search for it would lead to the most shocking experimental result in the history of physics, an experiment that would prove that everything they thought they knew about light, space, and time was wrong. And that's where our story takes its most dramatic turn, because the search for this invisible medium would ultimately reveal that the speed of light isn't just a measurement of how fast light travels. It's a measurement of something far more fundamental about the structure of reality itself. Chapter 1. The Fabric of Everything. The Search for the Medium. You know what's fascinating about waves? Every single wave you've ever experienced needs something to wave through. Sound waves need air to carry them to your ears. Ocean waves need water to crash against the shore. Water ripples need the surface of a pond to spread outward. This is so fundamental to how we understand reality that it seems impossible for a wave to exist without a medium to travel through. So when scientists in the 1800s realized that light behaves like a wave, they faced an unavoidable conclusion. Light must have a medium too. Something had to be carrying these light waves across the vast emptiness of space, allowing the sun's rays to reach Earth, letting starlight travel billions of miles to sparkle in our night sky. They called this mysterious substance the luminiferous ether. Think about how elegant this concept was. The ether had to be everywhere, filling every corner of the universe like an invisible ocean. It had to be incredibly thin, so thin that planets could move through it without any resistance. Yet it also had to be incredibly rigid, more rigid than steel, to carry light waves at such tremendous speeds. The ether became the foundation of physics. It explained everything: how light travelled through space, how electromagnetic waves propagated, how the universe held together as one connected whole. Scientists were so confident in its existence that they stopped questioning whether it was real and started focusing on its properties. How dense was it? How did it interact with matter? Could we detect its motion? But here's what makes this story so captivating. The ether seemed so obviously necessary, so logically required, that no one seriously considered the alternative. What if light didn't need a medium at all? What if everything we thought we knew about waves was incomplete? The very idea seemed absurd, impossible, a violation of common sense itself. The experiment that broke physics. In 1887, two American physicists, Albert Michelson and Edward Morley, decided to settle the ether question once and for all. They weren't trying to disprove the ether's existence, quite the opposite. They were absolutely certain it existed and wanted to measure Earth's motion through it with unprecedented precision. Here's the brilliant logic behind their experiment. Earth orbits the Sun at roughly 67,000 miles per hour. If the ether fills space like a cosmic ocean, then Earth must be moving through this ether at tremendous speed. Just like you feel wind when you stick your hand out of a moving car window, Earth should experience an ether wind as it rushes through this invisible medium. This ether wind should affect the speed of light in different directions. Light travelling in the same direction as Earth's motion should move slightly faster, carried along by the ether current. Light travelling perpendicular to Earth's motion should move at its normal speed. The difference would be tiny, but it should be measurable with the right equipment. Michelson and Morley built the most sensitive instrument ever created at that time. Their interferometer could detect changes in light's travel time smaller than a single wavelength. They split a beam of light, sent the two halves on perpendicular paths, then recombined them to create an interference pattern. If the ether wind existed, this pattern would shift as Earth moved through space. They tested their device in every season at every time of day, pointing it in every direction. They measured and remeasured with obsessive precision, and what they found shook the foundations of physics. There was no ether wind, none at all. Light travelled at exactly the same speed in every direction, regardless of Earth's motion through space. The scientific community was stunned. This wasn't just an unexpected result, it was impossible, according to everything they understood about waves and motion. If there's no ether wind, then either the ether doesn't exist or the laws of physics are fundamentally different than anyone imagined. The crisis of understanding. The Michelson-Morley experiment created what historians call a crisis in physics. When your most careful measurement contradicts your most basic assumptions, you have to question everything. Scientists proposed increasingly desperate explanations to save the ether theory, because abandoning it meant abandoning their entire understanding of how the universe works. Maybe Earth drags some of the ether along with it as it moves, creating a zone of calm around our planet. But this couldn't explain why light from distant stars reaches us at the same speed, regardless of Earth's orbital position. Maybe the ether has different properties near massive objects like planets and stars. But every test designed to detect these variations came up empty. The most intriguing proposal came from physicists Hendrik Lorentz and George Fitzgerald. They suggested that objects actually shrink when they move through the ether. Not just any shrinkage, but exactly the right amount to compensate for the ether wind. Michelson and Morley's interferometer arms were contracting just enough to hide the very effect they were trying to measure. This length contraction hypothesis was mathematically elegant and could explain the experimental results. But it raised disturbing questions. How could the ether know exactly how much to shrink objects? Why would this contraction be perfectly coordinated to hide all evidence of the ether's existence? It felt like the universe was conspiring to keep its secrets hidden. Some scientists even proposed that time itself might be affected by motion through the ether. Clocks might run differently depending on their speed and direction through this cosmic medium. But this idea seemed so radical, so far removed from everyday experience, that most physicists dismissed it as mathematical fantasy. The crisis deepened because every proposed solution created new problems. If objects contract when they move, why don't we feel ourselves shrinking as Earth orbits the Sun? If time changes with motion, why do all our clocks stay synchronized? If the ether has such strange properties, why can't we detect it through any other means? Enter the patent clerk. While the greatest minds in physics struggled with increasingly complex theories to save the ether, a 26-year-old patent clerk in Bern, Switzerland, was thinking about the problem from a completely different angle. Albert Einstein had no prestigious university position, no research laboratory, no access to the latest experimental equipment. What he had was an uncompromising commitment to logical thinking and the courage to follow his ideas wherever they led. Einstein realized that everyone was asking the wrong question. Instead of, how can we detect the ether? Or, why can't we measure Earth's motion through the ether? He asked something far more fundamental. What if the speed of light is always the same, no matter what? This wasn't just a slight modification of existing theory. It was a complete reversal of how physicists thought about motion and measurement. For centuries, speeds had been relative. If you're walking forward on a moving train, your speed relative to the ground is your walking speed plus the train speed. If you're walking backward on the train, your speed relative to the ground is the train speed minus your walking speed. This is so obvious, so intuitive, that questioning it seemed pointless. But Einstein took this questioning seriously. What if light doesn't follow these common-sense rules? What if light always travels at the same speed relative to every observer, regardless of how fast they're moving? This would mean that if you're racing toward a light beam at half the speed of light, the light still approaches you at its full speed, not at 1.5 times its normal speed. The idea seemed impossible, but Einstein followed its implications with relentless logic. If light speed is constant for all observers, then something else must be variable, something we had always assumed was fixed and absolute. Something so fundamental to our experience that questioning it felt like questioning reality itself. Einstein realized that space and time, the very stage on which all physics plays out, cannot be the rigid, unchanging backdrop that everyone assumed. If light speed is constant, then space must be flexible. Time must be elastic. The universe must be far stranger than anyone had ever imagined. This wasn't just a new theory about light. It was a complete reimagining of the nature of reality. Einstein was proposing that our most basic intuitions about space, time and motion are wrong. That the universe operates according to principles so foreign to everyday experience that they challenge the very foundations of common sense. The young patent clerk was about to publish a paper that would not only solve the ether crisis, but revolutionize our understanding of existence itself. He was about to show that the speed of light isn't just a speed. It's the speed at which reality operates, the cosmic speed limit that governs the very fabric of space and time. Chapter 2. When time becomes elastic. Everything you think you know about time is wrong. Not just a little wrong, but catastrophically, mind-bendingly wrong. The clock on your wall isn't measuring some universal constant ticking away the same for everyone everywhere. Time itself can stretch like taffy, compress like a spring, and even come to a complete standstill. And the key to understanding this cosmic illusion lies in the speed of light. We've discovered that light travels at an unbreakable speed limit. But here's what will blow your mind. That speed limit doesn't just govern how fast things can move through space, it governs how fast time itself can flow. The speed of light isn't just about light at all. It's about the fundamental nature of time and space, and once you understand this connection, you'll never look at reality the same way again. The postulate that changed everything. In 1905, a young Albert Einstein sat in his cramped office at the Swiss Patent Office, staring at what seemed like the simplest question in physics. What if the speed of light is the same for everyone, no matter how fast they're moving? This wasn't just a casual thought experiment. This was Einstein taking an axe to the foundation of physics itself. Think about what this means for just a moment. If you're standing still and measure the speed of light, you get 186,000 miles per second. If you're racing toward that same beam of light at half the speed of light, common sense says you should measure it going much faster, right? Like catching a baseball while running toward the pitcher. But Einstein said no, you'd still measure exactly 186,000 miles per second. This single assumption, this one simple postulate, would shatter our understanding of time, space, and reality itself. Because if light always travels at the same speed no matter what, then something else has to give. And that something else is time itself. Einstein paired this with another seemingly innocent assumption. The laws of physics work the same way everywhere in the universe. Drop a ball on Earth or on a spaceship travelling at 1 billion miles per hour, and gravity works exactly the same way. These two ideas together became the foundation of special relativity. But their consequences were so bizarre that even Einstein himself initially thought he must have made a mistake. Here's what's truly mind-blowing about this moment in history. Einstein didn't have access to particle accelerators or space telescopes or supercomputers. He had nothing but pure thought, mathematics, and an unwavering commitment to following logic wherever it led him. And where it led him was to the most shocking discovery in human history. Time is not what we think it is. The twin paradox unveiled. Let me tell you about two identical twins, Sarah and Emma, and the experiment that will prove time is not universal. Sarah decides to take a journey to Proxima Centauri, our nearest star neighbour, about 4 light-years away. She climbs aboard a spacecraft capable of travelling at 99% the speed of light. Emma stays behind on Earth. From Emma's perspective on Earth, Sarah's journey takes a little over 8 years. 4 years to reach Proxima Centauri, 4 years to return. Emma ages 8 years, celebrates 8 birthdays, watches 8 years of sunrises and sunsets. But here's where reality gets weird. When Sarah returns from her journey, she has aged only about 1 year. This isn't science fiction, this isn't a thought experiment, this is measurable, observable, documented reality. Time literally runs slower for Sarah because she's moving at nearly the speed of light. But here's the part that will really mess with your head. From Sarah's perspective, her clocks run perfectly normally. She doesn't feel like time is slowing down. To her, it's Emma and everyone on Earth whose clocks are running slowly. This phenomenon is called time dilation, and it's one of the most thoroughly tested predictions in all of physics. Every time you use GPS on your phone, the satellites orbiting Earth are experiencing time dilation. They're moving fast enough that their clocks run slightly slower than clocks on Earth's surface. If we didn't account for this time difference, your GPS would be off by miles within hours. But why does this happen? Why does moving fast through space slow down your passage through time? The answer lies in understanding that space and time aren't separate things at all. They're woven together into something called space-time, and the speed of light is the speed at which you can move through this combined fabric. Think of it this way. You're always moving through space-time at the speed of light, always. When you're sitting perfectly still, you're moving through time at maximum speed. But when you start moving through space, some of that motion gets redirected from time into space. The faster you move through space, the slower you move through time. At the speed of light, all your motion is through space, which means you're not moving through time at all. Time stops. Length contraction, the shrinking universe. Time dilation is just half the story. If time can stretch and compress, what happens to space itself when you approach the speed of light? The answer is equally mind-bending. Space shrinks. Let's go back to Sarah's spacecraft. As she accelerates toward the speed of light, something extraordinary happens. From Emma's perspective on Earth, Sarah's spacecraft begins to physically contract in the direction of motion. At 90% the speed of light, the spacecraft appears to be about half its original length. At 99% the speed of light, it's compressed to just 14% of its original length. At 99.9%, it's squeezed down to less than 5% of its original size. This isn't an optical illusion. This isn't the spacecraft being crushed by some external force. This is space itself being compressed. The spacecraft is actually shorter in the direction of motion. But here's what's truly bizarre. From Sarah's perspective, inside the spacecraft, everything appears perfectly normal. She doesn't feel compressed. The spacecraft doesn't look shorter to her. Instead, from her high-speed perspective, it's the entire universe in her direction of travel that appears compressed. This phenomenon is called length contraction, and it's the spatial companion to time dilation. Just as time dilates when you move fast through space, space itself contracts when you move fast through time. The faster you go, the more compressed the universe becomes in your direction of travel. Imagine Sarah looking out the window of her spacecraft as she approaches Proxima Centauri at 99.9% the speed of light. From her perspective, the 4-light-year journey to Proxima Centauri appears to be compressed to just about 2 months of travel distance. The space between Earth and Proxima Centauri literally shrinks from her perspective. This is why she experiences the journey as taking only about 1 year, while Emma experiences it as taking 8 years. But here's where your brain might start to hurt. Which perspective is correct? Is Sarah's spacecraft really contracted, or is the space between stars really compressed? Einstein's answer is both and neither. There is no absolute perspective. There is no universal reference frame. Reality depends on your point of view, and every point of view is equally valid. The energy barrier. We've seen that time slows down and space contracts as you approach the speed of light. But there's another effect that's even more important for understanding why nothing can break the light-speed barrier. Mass increases. Not just any mass increase, but an increase that becomes more and more dramatic as you approach light speed. At 50% the speed of light, your mass increases by about 15%. At 90% it nearly doubles. At 99% it increases by a factor of 7. At 99.9% it increases by a factor of 22. And as you approach exactly the speed of light, your mass approaches infinity. This is the real reason nothing with mass can reach the speed of light. It's not just that it would take a lot of energy, it would take infinite energy, more energy than exists in the entire universe. The universe simply doesn't have enough energy to accelerate any object with mass to the speed of light. Think about what this means. Every time you step on the gas pedal in your car, you're literally becoming more massive. The faster you go, the heavier you get. The effect is so small at everyday speeds that it's completely unmeasurable. But it's there. At highway speeds, you might be a few billionths of a gram heavier than when you're at rest. But that tiny effect scales up dramatically as you approach the cosmic speed limit. This isn't just about spacecraft and high-speed travel. This is about the fundamental structure of reality itself. The universe has built-in protection against breaking the speed of light. It's like a cosmic security system that makes it harder and harder to go faster the closer you get to the limit. But here's what's truly elegant about this cosmic security system. It's not arbitrary. It's not like the universe decided to impose a speed limit just to be difficult. The speed limit emerges naturally from the fundamental structure of space and time themselves. The speed of light isn't just a speed limit for objects moving through space. It's the speed limit for causality itself, why light gets to cheat. So far we've talked about what happens to objects with mass as they approach the speed of light. Time slows down, space contracts, mass increases toward infinity. But what about light itself? How does light manage to travel at the speed of light without requiring infinite energy? The answer is both simple and profound. Light has no mass. Zero. Not just very little mass, but literally no mass at all. A photon, the particle of light, is pure energy with no rest mass whatsoever. And this changes everything. Because light has no mass, it doesn't experience the mass increase that prevents other objects from reaching light speed. But there's something even more remarkable about massless particles. They can't travel at any speed other than the speed of light. They're born traveling at light speed. They live their entire existence at light speed, and they die at light speed. They can never slow down, never speed up, never come to rest. From the perspective of a photon, something even more mind-bending happens. Because photons travel at the speed of light, they experience maximum time dilation. From a photon's perspective, time doesn't pass at all. A photon that travels from the sun to Earth, a journey that takes about 8 minutes from our perspective, experiences that entire journey as instantaneous. From the photon's point of view, it's created at the sun and absorbed by your eye in the same moment, with no time passing in between. This leads to one of the most beautiful paradoxes in physics. From our perspective, light from distant galaxies has been traveling for billions of years to reach us. We're seeing ancient light from the early universe, snapshots of cosmic history. But from the perspective of those photons, they were created at the surface of ancient stars and absorbed by our telescopes in the same instant, with no time passage at all. Light experiences the entire history of the universe as a single moment. Every photon that has ever existed, from the cosmic microwave background radiation left over from the Big Bang to the light from your smartphone screen, exists in an eternal now from its own perspective. This is why light can travel at the speed of light while nothing else can. It's not cheating the system. It is the system. The speed of light isn't really about light at all. It's about the fundamental speed of causality, the speed at which cause and effect can propagate through the universe. Light just happens to be the most familiar thing that travels at this fundamental speed, the deeper truth. As we reach the end of our journey through the strange world of time dilation, length contraction, and the cosmic speed limit, we arrive at a truth that's both simple and profound. Einstein's special theory of relativity isn't really about relativity at all. It's about something absolute, the speed of light in a vacuum. Everything else in the universe is relative. Time depends on your speed. Distance depends on your motion. Mass depends on your velocity. But the speed of light is the same for everyone, everywhere, always. It's the one constant in a universe where everything else is variable. This leads us to a stunning realization about the nature of reality itself. The speed of light isn't just a speed limit for objects moving through space. It's the speed at which reality itself operates. It's the speed at which information can travel from one place to another. It's the speed at which cause and effect can propagate through the universe. When you flip a light switch, the electrical signal travels down the wire at a significant fraction of the speed of light. When you send a text message, the electromagnetic waves carrying your message travel at the speed of light. When you look at a star, you're receiving information that travelled to you at the speed of light. The speed of light is the speed of information itself. But we're not done yet. We've learned that space and time are flexible, that mass can increase, that nothing with mass can reach the speed of light. But this raises an even deeper question. What exactly is the speed of light the speed of? What is it that makes this particular speed so special that it governs the fundamental structure of space and time themselves? The answer to that question will take us even deeper into the heart of reality, to the very foundations of what space and time actually are. Because the speed of light isn't just about light, and it's not just about speed. It's about the fundamental nature of existence itself and the cosmic network that connects every point in the universe to every other point. The speed of light is the speed of space-time itself. And understanding what that means will change everything you think you know about the universe. Chapter 3. The Cosmic Speed of Information. What if I told you that every single moment of your life you're trapped inside an invisible prison? A prison so fundamental to reality that even light itself cannot escape its boundaries. This prison doesn't have walls made of steel or concrete. Instead, it's made of something far more powerful and inescapable. The very fabric of space and time itself. You see, the speed of light isn't just about how fast photons can travel through empty space. No, it's something far more profound and terrifying. The speed of light is actually the maximum speed at which information can travel through the universe. And that simple fact creates boundaries around your existence that are more absolute than any physical barrier ever could be. Every decision you make, every thought you think, every action you take exists within these invisible walls. And here's what will blow your mind. These walls are constantly expanding, but they're also permanently separating you from most of the universe. The question is, are you ready to discover just how small your actual universe really is? Space-time, the four-dimensional stage. Let me start by completely destroying everything you think you know about space and time. You've been living your entire life believing that space is just empty room where things happen and time is just the ticking of a clock. But that's not reality. That's not even close to reality. Space and time aren't separate things at all. They're woven together into a single four-dimensional fabric that physicists call space-time. Think about this for a moment. Right now, as you're listening to these words, you exist at a specific location in space, but you also exist at a specific moment in time. Those coordinates, your position in space and your position in time, are actually one unified thing. Einstein discovered that space and time are so interconnected that you cannot have one without the other. When you move through space, you're automatically moving through time. When time passes, you're moving through a fourth dimension that's just as real as length, width, and height. This isn't some abstract mathematical concept. This is the actual structure of reality. But here's where it gets mind-bending. In this four-dimensional space-time, there's a cosmic speed limit. And that speed limit is the speed of light. But it's not limiting how fast you can move through space. No, it's limiting how fast information can move through space-time itself. Every piece of information in the universe, every signal, every influence, every cause that wants to create an effect is trapped by this speed limit. This means that your reality, your actual experienced universe, is limited by how fast information can reach you. And that speed is exactly 299,792,458 meters per second. Not a single bit of information can travel faster than this, and this fact creates invisible boundaries around your existence that are more absolute than the laws of any government or the walls of any prison, causality's guardian. Now here's where things get absolutely terrifying, and I mean that in the most wonderful way possible. The speed of light doesn't just limit how fast things can happen. It's actually protecting the entire logical structure of the universe from complete collapse. You see, causality is the principle that causes must come before their effects. You drop a glass, then it breaks, you flip a light switch, then the light turns on, you send a text message, then your friend receives it. This seems obvious, right? But what would happen if information could travel faster than light? If signals could exceed light speed, then in certain reference frames, effects could actually precede their causes. You could receive a reply to an email before you sent it. You could see the glass hit the floor before you dropped it. You could know the outcome of a decision before you made it. The entire cause and effect structure that makes logic possible, that makes science possible, that makes rational thought possible, would crumble into paradox and contradiction. The speed of light is literally the guardian of causality. It's the cosmic speed limit that keeps the universe logically consistent. Every time a photon travels at exactly light speed, it's enforcing the rule that causes must precede effects. Every time information propagates through space-time at this maximum speed, it's preserving the rational structure of reality itself. But this protection comes at a cost. The cost is that you are permanently isolated from most of the universe. Most of what exists cannot influence you, and you cannot influence most of what exists. The speed of light creates a bubble around you, and everything outside that bubble might as well be in a completely different universe. The light cone, your universe's boundary. This is where we need to talk about one of the most profound concepts in all of physics, the light cone. And I want you to really understand this because it's going to change how you think about your place in the universe forever. Imagine that you're sitting exactly where you are right now at this exact moment. Now imagine that we could visualize space-time as a four-dimensional graph with 3 dimensions of space and 1 dimension of time. From your current position in space-time, we can draw something called a light cone. The light cone shows you every event in the universe that can possibly influence you and every event that you can possibly influence. The boundary of this cone is determined by light speed. Any event inside your past light cone could have sent you information because there was enough time for a light signal to travel from that event to you. Any event inside your future light cone can be influenced by you because there's enough time for you to send a light signal to that event. But here's the crucial part. Everything outside your light cone is completely disconnected from you. Events outside your light cone cannot influence you in any way, and you cannot influence them in any way. From your perspective, they might as well not exist. They are in what physicists call your elsewhere, regions of space-time that are causally disconnected from your existence. Let me give you some numbers that will make this real. The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. This means that if something happens on a planet orbiting Proxima Centauri right now, you won't be able to know about it for 4.2 years. And if you want to send a signal to that planet, it will take 4.2 years to get there. For those 4.2 years, you and that planet exist in each other's elsewhere. The Andromeda Galaxy is 2.5 million light-years away. If every star in Andromeda exploded right now, you wouldn't know about it for 2.5 million years. For the next 2.5 million years, you and the Andromeda Galaxy are completely causally disconnected. You exist in separate universes as far as information transfer is concerned. This means that your actual universe, the region of space-time that can causally interact with you, is much, much smaller than the observable universe. Most of what we can see through telescopes exists in our elsewhere. We can observe it, but we cannot communicate with it. We cannot influence it, and it cannot influence us, all because of the speed of light. Quantum entanglement, the apparent exception. Now, just when you think you understand the rules, physics throws you a curveball that seems to break everything we just talked about. It's called quantum entanglement, and Einstein absolutely hated it. He called it spooky action at a distance, and he spent years trying to prove it couldn't be real. Here's what happens in quantum entanglement. You can create two particles that become entangled, meaning their properties are mysteriously connected. If you measure one particle and find it spinning clockwise, the other particle will instantly be found spinning counterclockwise, no matter how far apart they are. And I mean instantly. If you separate these particles by billions of light years and measure one, the other responds immediately. This seems to violate everything we just learned about information being limited by light speed. How can the second particle know what happened to the first particle faster than light could travel between them? How can information about the measurement result travel instantaneously across the universe? But here's the beautiful and subtle truth. No information actually travels between the entangled particles. I know this sounds impossible, but stay with me. When you measure the first particle, you're not sending it a signal that forces it to have a particular spin. Instead, you're discovering a correlation that was already there, built into the quantum state, when the particles were first entangled. Think of it like this. Imagine you have two coins that are magically connected. When you flip one and it comes up heads, the other will always come up tails, no matter how far apart they are, but the outcome of each flip is still random. You can't control whether your coin comes up heads or tails, so you can't use this connection to send a message to the person with the other coin. Quantum entanglement works similarly. The correlations between the particles are real and instantaneous, but they're random correlations. You can't control what result you get when you measure your particle, so you can't use entanglement to send information faster than light. The speed of light barrier remains intact, but quantum mechanics reveals that reality is far stranger than we imagined. The entangled particles don't communicate with each other. Instead, they share a quantum state that transcends our normal concepts of space and time. This doesn't violate relativity, but it does reveal that the universe has layers of reality that operate according to rules we're only beginning to understand. The deeper implications. What we've discovered in this exploration is that the speed of light is far more than just a cosmic speed limit. It's the fundamental rate at which reality processes information. It's the speed at which cause and effect propagate through the universe. It's the boundary that defines what can influence what in the cosmic web of existence. Your light cone isn't just a mathematical abstraction, it's the actual boundary of your causal universe. Everything inside your light cone is potentially part of your story. It could influence you or be influenced by you. Everything outside your light cone exists in a parallel reality that you can never directly touch. This means that the universe is not one unified whole where everything is connected to everything else. Instead, It's a vast collection of overlapping causal domains, each limited by the speed of light. You exist in your domain, other civilizations exist in theirs, and the boundaries between these domains are constantly expanding as time moves forward and light cones grow larger. But here's what's truly beautiful about this. Even though you're trapped in your light cone, that boundary is always expanding. Every second, your causal domain grows larger by 300,000 kilometers in every direction. New regions of space-time are constantly entering your light cone, bringing new possibilities for connection and influence. The speed of light doesn't just isolate you from the universe. It also gradually connects you to more and more of the universe as time passes. It's both a prison and a key, both a barrier and a bridge. It separates you from most of reality while simultaneously being the mechanism by which you can eventually reach any point in space-time, given enough time. And that realization leads us to an even deeper question. If the speed of light is the universe's way of organizing information and maintaining causality, then what does this tell us about the fundamental nature of reality itself? Is the speed of light an arbitrary constant, or is it built into the deepest levels of existence? The answer will challenge everything you think you know about the nature of the universe itself. Chapter 4. The universe's source code. Every single atom in your body right now is vibrating according to a mysterious number that scientists have been obsessing over for nearly a century. This number, buried deep in the mathematics of reality itself, determines whether you can exist or whether the universe collapses into chaos. And here's the truly mind-bending part. This same number is secretly controlling the speed of light, which means it's controlling the very fabric of space and time around you as you watch this video. The number is approximately 1 divided by 137, and if it were even slightly different, we're talking about a change smaller than the width of a human hair compared to the distance from Earth to the Moon. You wouldn't be here, I wouldn't be here, and nothing in the universe would make sense. But why this number? Why not 1 divided by 50 or 1 divided by 1,000? And what does this have to do with why light can't go any faster than it does? What we're about to discover will fundamentally change how you see every beam of light, every electrical device, and every magnetic force around you. Because the speed of light isn't just some random cosmic speed limit that the universe arbitrarily chose. It's hardwired into the deepest level of reality's programming language, the fine structure constant. Let me tell you about the most important number you've never heard of. Scientists call it the fine structure constant, and it's represented by the Greek letter alpha. When physicists first discovered this number, they thought it was just a mathematical curiosity, a weird ratio that popped up in their equations about how atoms work. They had no idea they'd stumbled upon what many now consider to be the universe's most fundamental constant. Here's where it gets absolutely fascinating. This number shows up everywhere in physics, but it shows up without any units attached to it. Think about that for a moment. The speed of light has units, miles per second or meters per second. Temperature has units, degrees Celsius or Fahrenheit. Mass has units, pounds or kilograms, but the fine structure constant is just a pure number. It's the same whether you measure it on Earth, on Mars, or in a galaxy billions of light years away. It's dimensionless, which means it's truly fundamental to the structure of reality itself. Now, what does this number actually control? It determines how strongly light interacts with matter. Every time a photon of light hits an electron, every time an atom absorbs or emits light, every time you see anything at all, the strength of that interaction is governed by this mysterious constant. If alpha were larger, atoms would be more tightly bound together. If it were smaller, atoms would barely hold together at all. But here's the truly staggering part. Physicists have calculated what would happen if this number were different by even tiny amounts. If alpha were just 4% larger than it is, carbon atoms couldn't form the complex bonds necessary for organic chemistry. DNA wouldn't exist, proteins wouldn't exist. Life as we know it would be impossible. If alpha were just 10% smaller, hydrogen atoms would be so weakly bound that they'd fall apart under normal conditions. Stars couldn't burn hydrogen fuel, and the universe would be cold and dead. The fine structure constant is so perfectly tuned for complexity and life that it's almost as if someone carefully dialed it in. And yet we have no idea why it has the value it does. Richard Feynman, one of the greatest physicists who ever lived, called it one of the greatest damn mysteries of physics, and said that all good theoretical physicists should worry about this number and know how to calculate it. But more than half a century after Feynman said that, we still don't know where it comes from. What we do know is that this constant is intimately connected to the speed of light, and that connection reveals something profound about the nature of electromagnetic reality itself. Electric and magnetic, two faces of one force. To understand how the fine structure constant controls the speed of light, we need to dive into one of the most beautiful discoveries in all of physics, the realization that electricity and magnetism are actually the same force. This discovery literally changed the world, giving us everything from electric motors to radio waves to the device you're watching this video on right now. For centuries, scientists thought electricity and magnetism were completely separate phenomena. Sure, they noticed some weird connections. Rub a piece of amber with fur and it attracts small objects. That's static electricity. But magnets seem to work by completely different rules. They attracted iron, they had north and south poles, and they seemed to have nothing to do with the sparks you could generate by rubbing things together. Then, in the early 1800s, scientists started noticing something strange. Moving electrical charges created magnetic fields, and moving magnetic fields created electrical charges. It was as if these two forces were somehow talking to each other, creating each other in an endless conversation. The breakthrough came when James Clerk Maxwell wrote down 4 elegant equations that described both electricity and magnetism as aspects of a single unified electromagnetic field. These equations are so fundamental to our understanding of reality that they're carved in stone in universities around the world. And hidden within these equations was a shocking prediction that no one saw coming. When Maxwell combined his equations and solved them mathematically, he found that they predicted the existence of electromagnetic waves, ripples of electric and magnetic fields that create each other as they propagate through space. The electric field creates a magnetic field, which creates an electric field, which creates a magnetic field in an eternal dance that travels at a very specific speed. And when Maxwell calculated what that speed would be, he got a number that was shockingly familiar, approximately 186,000 miles per second. Light, Maxwell realized, wasn't some mysterious separate phenomenon. Light was an electromagnetic wave. Every rainbow, every sunset, every glimmer of starlight was actually oscillating electric and magnetic fields creating each other as they raced through space at the only speed they possibly could travel. But here's the truly mind-blowing part. The speed at which these electromagnetic waves travel isn't arbitrary. It falls directly out of 2 fundamental constants that describe how electric and magnetic fields behave in empty space. These constants, called the permittivity and permeability of free space, are like the electrical and magnetic properties of the vacuum itself. And when you combine these constants in just the right way, out pops the speed of light. But wait, it gets even more incredible. The fine structure constant that we talked about earlier, it's directly related to these same fundamental constants. In fact, you can think of the fine structure constant as measuring how electrically active the universe is at its most fundamental level. It determines how strongly electromagnetic fields interact with matter, which determines how atoms behave, which determines how light travels through space. This means that the speed of light isn't just some cosmic speed limit that was randomly chosen. It's the inevitable result of the electromagnetic structure of reality itself. Change the fine structure constant, and you change the speed of light. Change the speed of light, and you change the fundamental nature of how energy and information can flow through the universe. The vacuum, not empty. After all now, here's where our understanding of the speed of light takes a turn into the truly bizarre. When Maxwell talked about electromagnetic waves travelling through space, he was thinking of space as completely empty, a perfect vacuum with nothing in it at all. But modern quantum physics has revealed something that would have blown Maxwell's mind. Empty space isn't empty. It's actually seething with activity at levels so small and so fast that we can barely detect it. Welcome to the quantum vacuum, one of the strangest concepts in all of physics. According to quantum mechanics, even completely empty space is filled with what physicists call virtual particles. These aren't real particles in the sense that you could catch them or measure them directly. They're quantum fluctuations, brief flickers of energy that pop into existence and then disappear again so quickly that they don't violate the fundamental laws of physics. Think of it this way. The uncertainty principle of quantum mechanics says that you can't know both the exact energy and the exact time of any quantum system with perfect precision. This means that for incredibly brief moments, the universe can borrow energy from nowhere, create particle-antiparticle pairs out of nothing, and then have them annihilate each other and pay back the energy before anyone notices. It's like the universe is constantly writing itself tiny IOUs at the quantum level. These virtual particles aren't just a mathematical curiosity. They have real, measurable effects on the world around us. They create tiny forces that push metal plates together in laboratory experiments. They cause the energy levels of atoms to shift slightly from where they would be in a perfectly empty universe. And most importantly for our story, they give the vacuum itself electrical and magnetic properties. Remember those fundamental constants I mentioned, the permittivity and permeability of free space? These constants describe how responsive empty space is to electric and magnetic fields. But what quantum physics tells us is that this responsiveness comes from the virtual particles that are constantly popping in and out of existence in the vacuum. The quantum foam of virtual particles makes space itself act like a subtle electrical and magnetic medium. This is absolutely mind-blowing when you think about it. The speed of light, this fundamental constant that governs causality, information flow, and the structure of space-time itself, emerges from the quantum mechanical properties of empty space. The vacuum isn't a passive stage where physics happens. It's an active participant in the cosmic drama. It's quantum fluctuations setting the speed limit for how fast electromagnetic waves can propagate. In a very real sense, the speed of light is determined by how electrically thick the quantum vacuum is. If the virtual particles in the vacuum interacted more strongly with electromagnetic fields, light would travel slower. If they interacted more weakly, light could travel faster. The speed of light is literally the speed at which electromagnetic disturbances can propagate through the quantum foam that fills all of space. This gives us a completely new way to think about why nothing can go faster than light. It's not just that light sets an arbitrary speed limit, it's that the quantum structure of space itself can't process information any faster than the speed of light allows. The universe has a fundamental clock speed built into the fabric of reality, and that clock speed is determined by the quantum mechanical properties of empty space. Other universes, other speeds. This brings us to one of the most mind-bending questions in all of physics. Is our universe special? Could there be other universes out there with different fundamental constants, different fine structure constants, different speeds of light? And if so, what would those universes be like? Theoretical physicists have spent decades exploring this question, and the answers are both fascinating and deeply unsettling. It turns out that our universe appears to be balanced on a knife's edge of stability, with its fundamental constants tuned to incredibly precise values that allow for complexity, structure, and ultimately life itself. Let's imagine a universe where the fine structure constant was twice as large as it is in our reality. In this universe, electromagnetic interactions would be much stronger. Atoms would be more tightly bound together, which might sound like a good thing, but it would actually be catastrophic. The nuclear processes that power stars would be completely different. Hydrogen fusion might not work at all, or it might work so efficiently that stars would burn out in thousands of years instead of billions. The chemistry of complex molecules would be impossible, because electrons would be bound so tightly to atomic nuclei that they couldn't form the flexible bonds that make organic chemistry possible. Now imagine a universe where the fine structure constant was much smaller, say 10 times smaller than in our universe. Electromagnetic interactions would be incredibly weak. Atoms would barely hold together. The slightest thermal energy would tear electrons away from nuclei, making stable matter impossible, except at temperatures close to absolute zero. Chemical bonds wouldn't exist, molecules wouldn't form, and the universe would be filled with nothing but isolated atomic nuclei and free electrons. But it gets even stranger when we think about how changing the fine structure constant would affect the speed of light. Remember, these constants are all interconnected. Change the strength of electromagnetic interactions, and you change the electrical and magnetic properties of the vacuum, which changes the speed at which electromagnetic waves can propagate. In a universe with a larger fine structure constant, light might travel significantly slower than it does in our universe. This would have profound implications for causality and the flow of information. Events that seem simultaneous to us might be clearly separated in time in that universe. The size of light cones, the regions of space-time that can causally influence each other, would be much smaller. Distant parts of the universe would be even more isolated from each other than they are in our reality. Conversely, in a universe with a much smaller fine structure constant, light might travel faster, perhaps much faster. At first glance, this might seem like it would make for a more connected, more dynamic universe. But remember, faster light would come at the cost of weaker electromagnetic interactions, which means atoms wouldn't work properly. You'd have a universe where information could travel quickly, but there would be no stable structures to generate or receive that information. The more physicists study these hypothetical alternative universes, the more remarkable our own reality appears to be. The speed of light in our universe, 299,792,458 meters per second, isn't just some random number. It's intimately connected to a whole web of fundamental constants that seem to be perfectly balanced to allow for the existence of stable atoms, complex chemistry, long-lived stars, and ultimately the emergence of life and consciousness. Some physicists find this balance so improbable that they have proposed the existence of a multiverse, an infinite collection of universes with every possible combination of fundamental constants. In this view, we find ourselves in a universe with life-friendly constants, not because they were designed that way, but because we couldn't exist in any of the universes where the constants don't allow for complexity and life. Others argue that there might be deep physical principles we don't yet understand that require the fundamental constants to have the values they do. Perhaps there's only one mathematically consistent way for a universe to exist, and that way inevitably leads to the constants we observe. But regardless of which explanation turns out to be correct, the connection between the speed of light and the other fundamental constants reveals something profound about the nature of reality. The speed of light isn't just a speed limit. It's part of a tightly integrated system of physical laws that governs everything from the behavior of subatomic particles to the evolution of galaxies. The holographic principle. Now we come to perhaps the most mind-bending implication of our deep dive into the speed of light and the fundamental constants. Recent developments in theoretical physics suggest that our entire three-dimensional reality might be an illusion, a hologram projected from information stored on a two-dimensional surface, and the speed of light plays a crucial role in this cosmic projection system. This idea, known as the holographic principle, emerged from physicists trying to understand what happens to information when it falls into a black hole. The problem was this. According to quantum mechanics, information can never be truly destroyed. But according to general relativity, anything that falls past a black hole's event horizon is gone forever, seemingly taking its information with it. This created a paradox that threatened to undermine our understanding of both quantum mechanics and gravity. The resolution came from a startling realization. What if the information that falls into a black hole isn't actually destroyed, but instead gets encoded on the black hole's event horizon, its two-dimensional surface? From the outside, it would appear that the information disappears into the black hole, but in reality it would be stored as a kind of holographic encoding on the event horizon, with all the three-dimensional information compressed into a two-dimensional form. This led physicists to wonder, if black holes work this way, what about the universe as a whole? Could it be that all the information in any three-dimensional volume of space is actually encoded on the two-dimensional boundary that surrounds that volume? Could our entire perceived reality be a three-dimensional projection of information stored on some distant cosmic surface? The mathematics of this idea is incredibly complex, but the basic concept is similar to how a hologram works. When you look at a holographic image, you see a three-dimensional picture, even though the information is actually stored in a two-dimensional pattern of interference fringes. Change your viewing angle, and you see the three-dimensional scene from a different perspective, even though you're still looking at the same flat surface. According to the holographic principle, our universe might work in a similar way. All the information about every particle, every field, every event in our three-dimensional space might be encoded in a two-dimensional holographic pattern on some distant boundary. What we experience as three-dimensional reality would actually be a projection of this two-dimensional information. But here's where the speed of light becomes absolutely crucial to this picture. For a holographic universe to work, Information needs to be able to flow from the two-dimensional boundary to create the illusion of three-dimensional space. And that information can't travel faster than the speed of light. In fact, the speed of light might represent the fundamental processing speed of the cosmic holographic system, the rate at which the two-dimensional information can be transformed into our three-dimensional experience. Think of it this way. If the universe is like a cosmic computer running a three-dimensional simulation based on two-dimensional data, then the speed of light might be analogous to the clock speed of that computer's processor. Just as your computer can only update its display at a certain rate, the holographic universe can only update our three-dimensional reality at the speed of light. This perspective makes the speed of light's role as a universal speed limit even more profound. It's not just that nothing can travel faster than light through space, it's that space itself might be emerging from information processing that occurs at the speed of light. Every point in space, every moment in time, might be the result of holographic calculations happening at light speed on some distant cosmic boundary. The implications of this are staggering. It suggests that the speed of light isn't just a property of electromagnetic radiation, it's the fundamental rate at which reality itself is computed and projected. It's the universe's frame rate, the cosmic clock speed, that determines how quickly the holographic projection of space-time can be updated. If this picture is correct, then asking why the speed of light has the value it does is like asking why a computer processor runs at the speed it does. The answer involves the fundamental physical processes that drive the cosmic holographic projection system, processes that we're only just beginning to understand. This holographic view of reality also provides a new perspective on why the speed of light is connected to all the other fundamental constants we've discussed. If the universe is indeed a holographic projection, then all the constants that govern electromagnetic interactions, atomic structure, and the properties of the quantum vacuum are really parameters in the cosmic computation system. They're all aspects of the same underlying information processing system that creates our experienced reality. The speed of light, the fine structure constant, the properties of the quantum vacuum. They're all part of the universe's source code, the fundamental programming that determines how the holographic projection of reality operates. And just as changing the parameters in a computer program can dramatically alter the program's output, changing these fundamental constants would completely transform the nature of the holographic universe we experience, the speed of reality itself. As we reach the end of our journey into the universe's source code, we've discovered something truly extraordinary. The speed of light isn't really about light at all. It's about the fundamental rate at which reality processes information, the cosmic clock speed that governs how quickly the universe can update itself. From the mysterious fine structure, constant that determines how electromagnetic fields interact with matter, to the quantum foam of virtual particles that gives empty space its electrical properties, to the possibility that our entire three-dimensional reality is a holographic projection. Everything points to the same profound conclusion. The speed of light is hardwired into the deepest level of existence itself. When Einstein first proposed that nothing could travel faster than light, he thought he was describing a limit on motion through space. What we've discovered is far more profound. The speed of light appears to be the rate at which space and time themselves are generated, the fundamental frequency at which the universe computes reality. Every photon that hits your eye, every electrical signal in your brain, every electromagnetic wave that carries information through space, they're all travelling at the universe's processing speed, the rate at which existence itself unfolds. In a very real sense, We are living inside a cosmic information system, and the speed of light is that system's clock rate. This is why the speed of light can't be exceeded. It's not just that faster-than-light travel would violate causality or create paradoxes, though it would. It's that the speed of light represents the maximum rate at which the underlying reality generation system can operate. Going faster than light would be like trying to run a computer program faster than the computer's processor can execute instructions. It's not just difficult, it's meaningless. The next time you see light streaming through a window, or watch the glow of your phone screen, or marvel at the stars in the night sky, remember what you're really seeing. You're witnessing the universe's source code in action, the fundamental information processing that creates the reality we experience. The speed of light isn't just a cosmic speed limit, it's the speed of existence itself, the rate at which the universe dreams us into being. And that might be the most beautiful and profound truth we've ever discovered about the nature of reality. Chapter 5. Beyond the Limit. Every single law of physics has been tested, challenged, and sometimes broken. But there's one rule that seems absolutely unbreakable. Nothing can travel faster than the speed of light. Yet as we speak, there are galaxies racing away from you at speeds that would make light itself jealous. How is this possible? The answer will shatter everything you think you know about the universe's most sacred speed limit. The cosmic speed limit we've been exploring isn't just about light racing through space. It's about the fundamental structure of reality itself. But here's where things get mind-bending. The universe has found ways to appear to break its own rules, and understanding how reveals the deepest secrets about the nature of existence. The expanding universe paradox. Right now, as you're watching this video, there are countless galaxies speeding away from Earth at velocities that eclipse the speed of light. The Hubble Space Telescope has observed galaxies receding at more than twice light speed. Some theoretical models suggest galaxies at the edge of the observable universe are moving away from us at nearly 10 times the speed of light. This should be impossible. It violates everything we've learned about Einstein's cosmic speed limit. But here's the crucial insight that changes everything. These galaxies aren't actually moving through space faster than light. Instead, space itself is expanding, carrying these galaxies along like leaves on a flowing river. The difference is profound and reveals something extraordinary about the nature of space itself. When Einstein formulated his theory of relativity, he discovered that space and time aren't fixed, unchanging backdrops for cosmic events. They're dynamic, flexible, and can be stretched, compressed, and warped. The speed of light limit applies to objects moving through space, but it says nothing about space itself expanding or contracting. Think of it this way. If you're walking on a moving walkway at an airport, your speed relative to the ground is your walking speed plus the walkway's speed. But you're not violating any speed limits for walking because the walkway itself is moving. Similarly, galaxies can appear to exceed light speed because the space between us and them is expanding faster than light can travel across that expanding distance. This expansion isn't uniform either. The farther away a galaxy is, the faster it appears to recede from us. This relationship, known as Hubble's law, tells us that space itself is stretching everywhere simultaneously. Every cubic meter of space is getting bigger, and the cumulative effect over vast distances creates recession velocities that dwarf the speed of light. Inflation. When the universe broke its own rules. But the expanding universe we see today is nothing compared to what happened in the universe's first moments. During a period called cosmic inflation, space expanded so rapidly that it makes today's expansion look glacially slow. In less than a trillionth of a trillionth of a trillionth of a second after the Big Bang, the universe grew by a factor larger than 10, followed by 30 zeros. During inflation, regions of space that were once close enough to exchange light signals were suddenly separated by distances so vast that light would need longer than the age of the universe to travel between them. This didn't violate relativity because no information or matter actually travelled faster than light. Instead, the fabric of space itself was stretching exponentially, carrying distant regions beyond each other's reach forever. This inflationary expansion explains one of the biggest mysteries in cosmology: why the universe looks so uniform in all directions. The cosmic microwave background radiation, the afterglow of the Big Bang, has almost exactly the same temperature everywhere we look. Without inflation, opposite sides of the sky would never have been in contact with each other, so there's no reason they should have the same temperature. But inflation stretched a tiny uniform region to cosmic scales, explaining why the universe looks so homogeneous today. The physics driving inflation involves quantum fields with bizarre properties that we're still trying to understand. These fields can have negative pressure, which in Einstein's general relativity causes space to expand exponentially. During inflation, these quantum fields dominated the universe's energy density, driving the fastest expansion in cosmic history. Alcubierre drive, surfing space-time. If space itself can expand faster than light, could we harness this property for faster-than-light travel? In 1994, theoretical physicist Miguel Alcubierre proposed a revolutionary idea that doesn't violate relativity, but achieves faster-than-light travel by manipulating space-time itself. The Alcubierre drive works by contracting space in front of a spacecraft and expanding space behind it, creating a wave-like distortion in space-time that carries the ship along. From the perspective of someone inside the spacecraft, they never exceed the speed of light locally. They're just riding a wave of curved space-time that moves faster than light through the broader universe. Imagine you're on a surfboard riding a wave. You're not moving faster than the wave itself, but the wave carries you forward at its own speed. Similarly, an Alcubierre drive creates a warp bubble where the spacecraft remains stationary within the bubble, but the bubble itself moves through space faster than light. The mathematics of the Alcubierre drive are perfectly consistent with Einstein's general relativity. The equations work, and there's no violation of causality because information and matter within the warp bubble never exceed light speed locally. However, there's a massive catch that might make this forever impossible to build. The Alcubierre drive requires exotic matter with negative energy density, a form of matter that has never been observed and might not exist in nature. This exotic matter would need to have properties more bizarre than anything we've ever encountered. It would need to have negative mass, meaning it would fall upward in a gravitational field and would violate our understanding of quantum mechanics. Current estimates suggest that building an Alcubierre drive would require more exotic matter than exists in the observable universe. Some scientists have proposed modified versions that might require less exotic matter, but even these theoretical improvements would need technological capabilities far beyond anything we can imagine today. Quantum tunneling, the probabilistic escape. At the quantum scale, particles routinely perform feats that seem to violate the speed of light limit. Quantum tunneling allows particles to pass through barriers they shouldn't be able to cross, and some interpretations suggest they do so instantaneously, implying infinite speed. When a particle encounters a barrier, it doesn't have enough energy to overcome. Classical physics says it should bounce back. But quantum mechanics reveals that particles have a probability of appearing on the other side of the barrier without actually travelling through it. This quantum tunneling is essential for nuclear fusion in stars, radioactive decay, and the operation of many electronic devices. Some experiments have measured the time it takes for particles to tunnel through barriers and found results suggesting the process happens faster than light speed would allow. If a photon had to travel the same distance the particle tunneled, it would take longer than the measured tunneling time. This has led to speculation that quantum tunneling might provide a mechanism for faster-than-light communication. However, careful analysis reveals that no information actually travels faster than light during quantum tunneling. The particle doesn't have a well-defined path through the barrier, and you can't use tunneling to send a message faster than light. The apparent faster-than-light tunneling is a consequence of the quantum mechanical uncertainty principle, which says that particles don't have definite positions until they're measured. The key insight is that quantum mechanics is fundamentally probabilistic. When we say a particle tunnels through a barrier, we're really saying there's a probability amplitude for finding the particle on the other side. This probability doesn't travel through space in the classical sense, so it doesn't violate the speed of light limit for information transmission. The information paradox. Black holes create one of the most profound puzzles in modern physics, and it's intimately connected to the speed of light and information flow. When matter falls into a black hole, it crosses the event horizon, the point of no return beyond which not even light can escape. According to general relativity, this information is lost forever, trapped inside the black hole where it can never influence the outside universe. But quantum mechanics has an ironclad rule. Information can never be destroyed. Every quantum process is reversible in principle, meaning that if you knew the exact quantum state of every particle in the universe, you could run time backward and reconstruct any past state. This principle is so fundamental that violating it would undermine the mathematical consistency of quantum mechanics itself. The black hole information paradox arises because these two principles seem incompatible. General relativity says information can be permanently lost in black holes, while quantum mechanics says information must always be preserved. Stephen Hawking spent decades working on this problem and initially argued that information really is destroyed by black holes, violating quantum mechanics. However, Hawking later changed his mind based on insights from string theory and the holographic principle. The resolution might involve the idea that all the information falling into a black hole is actually encoded on the black hole's surface, its event horizon. From this perspective, information never actually crosses the event horizon, but instead becomes scrambled and encoded in Hawking radiation emitted by the black hole. This encoding process happens at the speed of light, which emerges as the fundamental rate at which information can be processed and transmitted in the universe. The black hole information paradox reveals that the speed of light isn't just about motion through space, it's about the fundamental limits on how quickly information can be manipulated and transformed in the quantum realm. Tachyons, the hypothetical speedsters. What if particles existed that always travelled faster than light? These hypothetical particles, called tachyons, would live in a mirror universe where the speed of light is a lower limit rather than an upper limit. Tachyons would need infinite energy to slow down to light speed, just as normal particles need infinite energy to speed up to light speed. The mathematical properties of tachyons are deeply bizarre. They would have imaginary mass, not just negative mass, but mass expressed as an imaginary number involving the square root of -1. Their energy would decrease as their speed increased, and they would experience time running backward compared to normal matter. If tachyons existed, they would create devastating paradoxes that would unravel the logical structure of space-time. You could use tachyons to send messages to the past, creating grandfather paradox situations where effects precede their causes. You could receive stock market information from tomorrow or warning messages about disasters that haven't happened yet. These causality violations aren't just philosophical problems. They would make the universe mathematically inconsistent. The equations of physics would have multiple solutions or no solutions at all. Events could be both caused and uncaused simultaneously, creating logical contradictions that would make rational understanding of the universe impossible. Most physicists believe tachyons cannot exist precisely because they would destroy the causal structure that makes physics possible. The speed of light emerges as more than just a speed limit. It's the boundary that separates the possible from the impossible, the consistent from the paradoxical, the rational from the absurd. Interestingly, some quantum field theories do predict tachyonic particles, but these predictions are interpreted as signs that the theory is unstable and will evolve to eliminate the tachyons. Tachyonic fields in these theories represent unstable vacuum states that decay into stable configurations without faster-than-light particles. The final answer. After exploring all these apparent exceptions and theoretical possibilities, we arrive at a profound realization. The speed of light isn't really about light at all. It's the speed of causality itself, the rate at which cause and effect can propagate through the universe. It's the speed at which information can travel, the maximum rate at which the universe can update itself from one moment to the next. Every interaction in the universe, from the collision of subatomic particles to the merger of galactic clusters, is governed by this fundamental speed limit. Electromagnetic forces that hold atoms together, the weak nuclear force that powers stellar fusion, and even the strong nuclear force that binds protons and neutrons all propagate at the speed of light. In quantum field theory, the speed of light emerges as the speed at which quantum fields can transmit information. When an electron changes its quantum state, that information about the change propagates outward at light speed, influencing other particles and fields. The speed of light is literally the speed at which reality updates itself. This perspective reveals why the speed of light is so fundamental that it appears in equations throughout physics, even those that seem to have nothing to do with light. It appears in Einstein's famous equation E/mc2, in the uncertainty principle of quantum mechanics, in the equations describing black hole thermodynamics, and in theories attempting to unify all the forces of nature. The speed of light is the universe's clock speed, the fundamental rate at which existence operates. Just as a computer's processor has a maximum speed at which it can execute instructions, the universe has a maximum speed at which it can process changes in the quantum fields that constitute reality. When we ask why nothing can go faster than light, we are really asking why the universe processes information at this particular rate rather than faster or slower. This question touches on the deepest mysteries of physics, why the fundamental constants have the values they do, why the universe exists rather than not existing, and why it operates according to mathematical laws that our minds can comprehend. The cosmic speed limit we've been exploring isn't a restriction imposed on the universe from outside. It emerges from the internal logic of space-time itself, from the mathematical structure that makes existence possible. In a very real sense, the speed of light is the speed at which being itself unfolds from moment to moment, the rhythm at which the cosmic symphony of existence plays out across space and time. Understanding this reveals that our original question about why light has a speed limit was backwards. Light doesn't set the cosmic speed limit. The cosmic speed limit determines how fast light can travel. The speed we call the speed of light is really the speed of existence itself, and light simply travels at the maximum speed that reality allows. This is why every attempt to exceed the speed of light either fails or reveals that what seemed like faster-than-light travel was actually something else entirely. The universe doesn't just forbid faster-than-light travel. It makes it logically impossible, mathematically inconsistent and physically meaningless. The speed of light isn't just a law of physics, it's a law of existence itself. End of Chapter 6. Script. Conclusion. The speed of wonder. We began this journey with a simple question that haunted a young Einstein. What happens when you're travelling at the speed of light and turn on your headlights? Now, after exploring the deepest mysteries of physics, we can finally answer that question. But the answer reveals something far more profound than Einstein could have imagined when he first posed this puzzle over a century ago. If you could somehow reach the speed of light and flip on your headlights, those photons would still race away from you at exactly 186,282 miles per second. Not because of some strange property of light, but because you've just discovered the fundamental rate at which the universe processes reality itself. The headlights would shine forward at light speed, because that's the speed at which existence unfolds moment by moment throughout the cosmos. This isn't just a quirk of physics, it's a window into the deepest nature of what it means to exist. The speed of light is the speed of causality, the speed of information, the speed of change itself. It's the universe's heartbeat, the rhythm at which reality updates from one instant to the next, the cosmic perspective. Every single moment of your life, you're surrounded by processes operating at the speed of light. The electrical signals racing through your brain right now, carrying thoughts and memories, are limited by this cosmic speed limit. The electromagnetic forces holding every atom in your body together propagate at exactly light speed. The photons striking your eyes, allowing you to see these words, travelled from your screen at precisely 299,792,458 meters per second. When you flip a light switch, the electrical signal doesn't travel instantly through the wire. It propagates at about 2/3 the speed of light, limited by the electromagnetic properties of the copper conductor. When you send a text message, that information races through fiber optic cables as pulses of light, carrying your words at the universe's maximum speed for information transfer. The GPS satellites orbiting overhead must account for both special and general relativistic effects related to the speed of light. Time runs slightly faster for these satellites due to their weaker gravitational field, and slightly slower due to their orbital velocity. Without correcting for these light speed-related effects, GPS would be off by miles within hours. Even the chemical reactions in your cells are governed by the speed of light. When electrons jump between energy levels in atoms, when molecules vibrate and rotate, when DNA replicates itself, all of these processes involve electromagnetic interactions that propagate at light speed. You are, quite literally, a being made of light speed processes living in a universe where light speed is the tempo of existence itself, living at the speed of light. The atoms that make up your body were forged in the nuclear furnaces of ancient stars. Those stellar reactions occurred at light speed, governed by the electromagnetic and weak nuclear forces that propagate at exactly c. The photons that carried energy from those stellar cores to their surfaces travelled for thousands of years at light speed before finally escaping into space. Some of those photons travelled across the galaxy for millions of years, still at light speed, before striking Earth's atmosphere. Plants captured some of this stellar energy through photosynthesis, another light-speed electromagnetic process, and converted it into chemical energy. That energy eventually became part of the food chain, part of the energy that powers your brain, part of the thoughts you're thinking right now, the carbon in your muscles, the oxygen in your blood, the calcium in your bones. All of it was created in stellar cores through nuclear processes operating at light speed, then dispersed through space in stellar winds and supernovas, travelling at significant fractions of light speed. You are literally made of star stuff, forged in light-speed processes and delivered to Earth by light-speed phenomena. The very act of thinking involves billions of neurons communicating through electrical signals that propagate at roughly half the speed of light through your nervous system. The speed of light doesn't just govern distant galaxies and exotic physics. It governs the speed of your thoughts, the rate at which your consciousness processes information, the tempo at which your awareness unfolds, the continuing mystery. Despite everything we've learned about the speed of light, profound mysteries remain. We know that light travels at 299,792,458 meters per second in vacuum. But we don't fully understand why this particular speed, rather than some other value. We know this speed is connected to the fundamental structure of space-time, but we don't know why space-time has the particular geometry it does. Recent discoveries in cosmology suggest that the expansion of space itself might be accelerating, driven by mysterious dark energy that makes up about 70% of the universe. This acceleration is happening at rates related to the speed of light, but we don't understand what dark energy is or why it has the strength it does. Quantum mechanics and general relativity, our two most successful theories of physics, both involve the speed of light in fundamental ways, but they give different descriptions of reality at the smallest scales. String theory and other attempts to unify these theories predict that space and time themselves might be emergent properties of more fundamental structures operating at scales where the speed of light takes on new meaning. Some theories suggest that the speed of light might not be truly constant, but could vary slightly across cosmic time or in the presence of certain exotic matter configurations. If true, this would revolutionize our understanding of physics and cosmology. Other theories propose that space and time are discrete, rather than continuous, made up of tiny pixels of space-time that limit the speed of light, just as the refresh rate of a computer screen limits how quickly images can change. The search for quantum gravity, a theory that describes how gravity works at the smallest scales, continues to reveal new mysteries about the speed of light. Some approaches suggest that space and time emerge from quantum entanglement operating at light speed. Others propose that information itself is more fundamental than matter and energy, with the speed of light representing the maximum rate at which information can be processed by the universe. The ultimate question. As we push the boundaries of physics with gravitational wave detectors that can measure distortions in space-time smaller than a proton, with quantum computers that manipulate information at the speed of light, and with particle accelerators that probe the fundamental structure of matter and energy, we continue to discover new depths to the mystery of the cosmic speed limit. Perhaps the most profound realization from our journey is that asking why light travels at the speed it does is really asking why the universe exists the way it does. The speed of light isn't just a number we've measured. It's built into the fundamental equations that describe reality. It emerges from the structure of space-time itself, from the properties of quantum fields, from the mathematical relationships that make existence possible. This suggests that the speed of light might not be arbitrary but necessary, that a universe with a different light speed might be mathematically inconsistent or physically impossible. Some theories propose that the speed of light is determined by the geometry of higher dimensional spaces that we can't directly perceive. Others suggest that it's related to the fundamental limits on information processing in any possible universe. The speed of light connects the smallest quantum processes to the largest cosmic structures. It links the firing of neurons in your brain to the expansion of the universe itself. It reveals that what we call light speed is really the speed of existence, the rate at which being itself unfolds across space and time. When we study the speed of light, we're not just learning about photons racing through space. We're discovering the fundamental rhythm of reality, the cosmic tempo that governs everything from the quantum foam of space-time to the evolution of galaxies. We're participating in the universe's attempt to understand itself, using patterns of light in our brains to comprehend the nature of light itself. The speed of wonder. The ancient Greeks believed that vision worked by light rays shooting from our eyes to illuminate the world around us. They were wrong about the mechanism, but they intuited something profound. There is indeed a deep connection between light and consciousness, between the speed of light and the speed of understanding. Every moment of wonder you experience, every aha moment when a difficult concept suddenly makes sense, every instant of awe when contemplating the cosmos. These experiences involve light-speed processes in your brain. The speed of light is literally the speed at which wonder travels from the external universe to your inner awareness. When you look up at the night sky, you're seeing light that has traveled for years, decades, or even millions of years to reach your eyes. You're directly observing the past, watching the universe as it was when that light began its journey to you. The speed of light doesn't just govern physics. It governs the very possibility of cosmic awareness, the ability to know that we're part of something vast and ancient and beautiful. The photons entering your eyes right now began their journey at the speed of light, carrying information about distant stars and galaxies. They've travelled across the cosmos at exactly 299,792,458 meters per second, maintaining their speed through the vacuum of space, through Earth's atmosphere, through the lens of your eye, until they strike your retina and trigger the electrical signals that will race through your optic nerve to your brain at roughly half the speed of light. In your brain, these signals will be processed by networks of neurons communicating at light-speed electromagnetic frequencies, creating the conscious experience of seeing starlight. The information that began its journey years ago at the speed of light will complete its journey in your awareness at the speed of thought, which is itself limited by the speed of light. This is the deepest magic of the cosmic speed limit. It's not just a constraint on how fast things can move. It's the fundamental rate at which information, wonder, and awareness can propagate through the universe. The speed of light is the speed at which the cosmos can know itself. The rate at which beauty and truth and understanding can travel from the far reaches of space and time into the miraculous 3 pounds of neural tissue that constitute your conscious mind. every ray of sunlight streaming through your window, every photon from a distant star, every glow from the screen you're watching right now carries with it the deepest secrets of reality. The speed of light isn't just the universe's speed limit. It's the speed at which wonder itself travels from the cosmos to your consciousness. The rate at which the universe shares its secrets with anyone curious enough to look up at the night sky and ask why. In the end, the speed of light teaches us that we're not separate from the universe we study. We're part of it, made of it, connected to it by the same fundamental forces and speeds that govern distant galaxies. The light-speed processes in our brains allow us to comprehend light-speed processes in the cosmos. We are the universe becoming aware of itself, using the speed of light to understand the speed of light, participating in the greatest adventure of all, the cosmic journey of existence, coming to know its own deepest nature. And that journey, like light itself, continues at exactly 299,792,458 meters per second, the speed of wonder, the speed of discovery, the speed of existence itself.